Hi there guys, welcome to another video where we take a look at another interesting problem in mathematics and where we take a look at the problem solving process, how that works, how it looks, what kind of things you might need to think about, you might benefit from thinking about when you're approaching a non-routine problem in mathematics and you're trying to find a solution to it. This is a fairly new YouTube channel. I've got only a few subscribers at the time of making this video, so I'd really appreciate it if you would hit the subscribe button and give this video a thumbs up, give it a like, maybe leave a comment in the comment section and show your support for this channel. I'm trying to reach a wider audience with this YouTube channel, so if you wouldn't mind telling other people about this channel as well, that would be much appreciated. So let's have a look at the problem that I've chosen for this particular video. So the problem that I've chosen is actually one that I thought, well, I didn't think of it myself. It's not an original problem, but it was something that I thought of attempting to solve as I was reading this book. So this is a book, a very famous book by Polya, How to Solve It. So if you are interested in developing your problem solving skills in mathematics, this is a really good book by a top mathematician. So this is not just anybody that wrote this. Polya was a superior mathematician. So you're getting a lot of good insight from somebody who really knew his stuff when it came to solving problems in mathematics. So the problem that I've chosen is the following: that if we've got a triangle and we draw the median lines in for that triangle, that the median lines are concurrent. In other words, the three median lines intersect at a single point. So let's have a look at this, a picture of what this might look like. So this is my triangle. A median line is a line drawn from, say, this vertex here to the midpoint of the line of the side opposite that particular angle or that particular vertex. So this is a median line. It's supposed to be straight. Okay, that's one median line, and then we can draw another median line in here. Again, it could be drawn a bit better. And then the third one is that one there. And what we're trying to prove is that these all intersect at a single point. So obviously from my diagram, it looks like they do, but as we're aware in mathematics, just because something looks a certain way in a diagram doesn't mean that that's how it is. Okay? We still need to go through the logical reasoning in order to obtain a satisfactory proof of our claim. So we can't just look at a diagram and say, well, it looks like they go through the same point, therefore they must. Because that just might be an accidental feature of this particular triangle. And if we might have to draw many triangles potentially before we come across one where this doesn't happen. What we're trying to prove, though, is that this happens in all cases. And we're going to have to use much more sophisticated machinery in order to prove that. Now, I've chosen this not because it's a terribly difficult problem, it's just there's different approaches that you can take to solving this problem. Two, in my opinion, completely different approaches. So one is based on coordinate geometry, and the other is based on pure geometry. Okay, so thinking about how I would have personally approached this problem, let's say when I was doing A-level maths. If I was asked to prove that the three medians of a triangle intersect or a concurrent or intersect at a single point, I would almost certainly have gone for a coordinate geometry approach. That's the approach that I'm going to go through first. How can we use coordinate geometry to prove this? But now, if I were to attempt this problem, in fact, I did that when I sat down to do this problem, my instincts told me to go for a more pure geometry. So using ratio and proportion and similarity and congruence and ideas like this, the kind of things that you see in Euclid's Elements or Apollonius's Conics, for example. And to me, the latter in this particular case is much more effective. It gives a much more straightforward, much more elegant solution. And that all I want to try to point out is that different approaches can sometimes, if you consider different approaches, you might open up more possibility, the possibility that you find a more elegant solution. So in this particular case, in my opinion, the coordinate geometry approach is too messy. It's much messier. Having said that, there are a lot of situations where coordinate geometry is the only real possibility that you have. And I'm not going to suggest at all that coordinate geometry, or analytic geometry as it might be called, is something that should be shunned or that it's inferior. It's not. There's a reason why coordinate geometry is kind of the dominant form of geometry in contemporary mathematics, because it is in so many ways far superior. It's much more adaptable to new contexts, new situations, and it deals with a much greater range of geometrical objects than pure geometry could hope to deal with. So let's have a look at this then. So let's say, just for sake of argument, let's assume that one of the vertices of our triangle is at the origin 0, 0, and the other is somewhere on the x-axis, A, 0. And then we've got another point which is at PQ. Okay, so, and then we consider the lines. So we've got this line, which we're going to call, I want to make sure that I'm consistent with my notes. So I've said that this is the line L1, that this median lies on the line L1, this median lies on the line L2, and this median lies on the line L3. Okay, and just so we know, this point has coordinates half A, 0. This point has coordinates, let me get this right, half A plus P, half Q. And this point has coordinates half P, half Q. Oh, half P, half Q. Okay. So these are easy to find. If you want to find the coordinates of the midpoint of a line segment, it's just the x coordinate of the midpoint is just the arithmetic mean of the x coordinates of the two endpoints, and the y coordinate of the midpoint is going to be the arithmetic mean of the y coordinates of the endpoints. Okay, so that's how I've got these here. Anybody that's done GCSE maths, A-level maths, will know how to find the midpoint of a line segment. Okay, time for a quick sip of coffee. You can hit the subscribe button, by the way, while I'm just having my coffee. That'd be great. Cheers. Okay, so the obvious method to go for here is to find the equations of L1, L2, L3 and show that they all intersect at this, that pairwise they intersect at the same point. So in other words, L1, the lines L1 and L2 will intersect at a certain point, and the lines L1 and L3 will intersect at a certain point, but they're the same point. Okay, so first thing I need to do then is to find the equations of these lines. So the gradient of L1, for example, is going to be, I'm not going to go through all of the steps of the calculation, it's 2q over 2p minus a. And therefore the equation of L1 is, again, I'm going to skip a few of the steps, but it's going to be y equals q over 2p minus a, that's the gradient, times 2x minus a. Okay, and then similarly for L2, we've got the gradient is q over a plus p, and the equation of L2 is y equals q over a plus p times x. And finally L3, the gradient is q over p minus 2a, and the equation of L3 is y equals q over p minus 2a times x minus a. Okay, so this is all elementary geometry. Anybody that's done, again, GCSE maths or even a couple of months of A-level maths will be able to do the necessary calculations to arrive at these results. So there's nothing particularly complicated. So then what I do is I find the intersection, the point of intersection of L. So what did I do first? L1 and L2. Yeah. Of L1 and L2. And you just solve with simultaneous equations. So we've already got y equals this and y equals this. So just set this equal to this and solve the equation. Again, I'm not going to go through all of the details. The first time I did this, I messed it up. And this is one of the things with using coordinate geometry sometimes, is that it's very easy to muck up somewhere. Maybe you end up with, like here, for example, I might end up with 2p plus a or something like that, or just something that throws the whole calculation out. And it's a pain when that happens, but it does happen. It's one of the drawbacks of using coordinate geometry. But like I said, coordinate geometry is a very powerful technique to use, but it's just one of those things. Okay, so the intersection of L1 and L2, we find the x coordinate is equal to a plus p over 3, and the y coordinate is equal to q over 3. Yeah, q over 3. Okay. Again, solving simultaneous equations, easy peasy, lemon squeezy, nothing to worry about. And then I looked at the point of intersection of L2 and L3. Okay, and I got the same results. The coordinates of the point of intersection of L2 and L3 are x equals a plus p over 3, y equals q over 3. No surprises there. This is exactly what I needed to show. That L1 and L2 intersect at a certain point. L2 and L3 intersect at a certain point, but the point where L1 and L2 intersect is the same as the point where L2 and L3 intersect. And therefore, the point where L1 and L3 intersect is also going to have the same, it's going to be the same coordinates, because two straight lines, two non-parallel straight lines can only intersect at a single point. Okay, so we don't need to worry about there being potentially multiple points of intersection. So this is one way that we can prove that the medians of a triangle are concurrent. Now you might argue, but this is a very particular case because you've chosen 0, 0, A0, so one of the sides to be on the x-axis. And I claim that this doesn't really change anything. This doesn't affect the result in any significant way. So as mathematicians are apt to say sometimes, without loss of generality, we can make this assumption. Now, if you think that this does affect the result in some way, then by all means, go ahead, try to formulate the problem in a much more general sense. And what you'll find is that you do end up with the same result. It's just, it's going to take you a bit more work to get there. But if you are in any way concerned about this assumption that I've made, that of placing this on the x-axis, then here's the idea, the general idea that you need to follow, and I urge you to have a go at it. So what we're going to have a look at next is the approach of solving this problem from the perspective of pure geometry. So let's have a look at the pure geometrical solution, or a pure geometrical solution to this problem, showing that the medians of a triangle are all concurrent. They all intersect at a single point. So pure geometry is something that is kind of neglected now in contemporary mathematics. What we mean by pure geometry is the kind of geometry that is exemplified in, for example, Euclid's Elements, Apollonius's conics, to a certain extent in Archimedes, and was the dominant form of geometry up to maybe the 19th century, when coordinate geometry really started to take over. And the reason for that is that coordinate geometry is much more versatile, applies to a much greater range of geometrical forms, geometrical objects. So whereas pure geometry is restricted to quite simple forms like circles, polygons, straight lines, planes, plane geometry, it can deal with things like parabolas, hyperbolas, ellipses. If you start looking at Apollonius, for example, it can also deal with things like hyperboloids, paraboloids, if you look at Archimedes. But really, it's restricted to these forms. Once you start getting onto much more complicated curves, then pure geometry really it just can't match up to analytic or coordinate geometry. But even Isaac Newton, for example, formulated a lot of his famous works in a pure geometric form. It is very powerful, and what I like about pure geometry is it's how simple ideas involving ratio and proportion can be used in very, very clever ways, very subtle ways to achieve some quite interesting relationships that using coordinate geometry would be very fussy, would be much more fiddly. But like I say, coordinate geometry is kind of the dominant form of geometry now, and understandably so, because it's much more versatile. And I don't at all suggest that it's an error or anything like that, that pure geometry is kind of neglected. It does come up, by the way, more when you do maybe GCSE maths, when you do things like circle theorems and congruence and similarity, these kinds of ideas. Oh, and when you do angles, if you've got parallel lines and lines intersecting parallel lines and things like you've got alternate angles and corresponding angles and things like that. These ideas come from pure geometry, and the first few books of Euclid's Elements would establish a lot of these facts as theorems or propositions in Euclid's Elements. It's a shame that pure geometry is kind of neglected, I guess, because it does have a certain charm to it, but it's not very practical. So it's one of the reasons why I completely understand why coordinate geometry really is taken over as the dominant form of geometry. So let's have a look at, let's draw our triangle. I'm going to draw it quite large. And let's label this A, B, C. And we've got the midpoints of these lines, of these sides, X, Y, Z maybe. And okay, which ones did I draw? Okay, so let's draw this median and this median, just for the time being. So I'm just going to take two of the medians initially, because I want to prove a certain result, and then we'll look at another pair of medians. But I also want to draw in on this diagram the line joining the midpoints of the sides AB and BC. So it'd be worth noting that this line that I've just drawn is going to be parallel to AC. So let's label these up as well. So we've got X, Y, Z, and P and Q. So we can see that XZ is parallel to AC. Okay, so we can see that angle XPQ is equal to angle YPC. Okay, when two lines intersect, for example, these two angles are going to be opposite angles. I can't remember. There's all sorts of names that get applied to it. There's maybe opposite angles. They're going to be equal. Angle QXP is going to be equal to angle YCP. So how do I know? Well, that's because XZ and AC are parallel. So parallel lines, what are these? Alternate angles. That's what we've got here, alternate angles. Alternate angles are equal. Okay. And finally, because the angles in a triangle always add up to two right angles, and therefore if two of the angles in this triangle, so we're talking about triangle XPQ on the one hand and triangle XPQ and CPY on the other hand, because two of the angles in XPQ are equal to two of the angles in CPY, that means that the third angles must also be equal. So angle, which one's left? XQP must be equal to angle CYP. So what does that mean? This means that triangle XPQ is similar to triangle CPY. So I'll just use this symbol to indicate similarity. Okay, so now because X and Z are the midpoints of these sides, that means that AC is going to be equal to twice XZ, for example. Okay, and Q is also the midpoint of XZ. Q is the midpoint of XZ. And Y is the midpoint of AC. Okay, so that means that the ratio, to XQ is going to be equal to YC. Therefore, by similarity, we get that 2XP is equal to PC. Okay, so in other words, if we think about this line from C to X, then the point P is going to be 2/3 of the way along that line from C, or that line segment, should I say, from C. Okay, so P is 2/3 of the way along this line segment from C. So that means that it's 1/3 of the way along the line segment from X, naturally. Okay, so that's established that result. So now let's have a look at some other. We've not finished yet, by the way. We're not finished. But I'm going to try to draw the same triangle, if I can. And which medians? Right, I want to stick with, we've got A, B, C. I want to stick with that median. And now I want to draw in this median. So that's X, this is Y, this is Z. And I want to draw this line in here in an analogous way to what I did over here. And I want this to be Q primed and this to be P primed. Okay, so I'm not assuming that p primed at this stage is the same as p. I'm assuming, or at least accepting the possibility, that the medians cx and az, which do intersect, will intersect at potentially a different point to that which the median cx and by intersect. Okay, so I can go through a similar line of reasoning here, so that I arrive at the result that the triangle AYQ, is this right? AY, no, this is not right. AYP primed, sorry, AYP primed is similar. So I've got to get my bearings a little bit here. XC. Okay, so yeah, it's similar to triangle. So XP. Right. Okay, getting completely muddled up here. Okay, so it's the triangle AXP primed, which is going to be similar. Again, I'm using this symbol just to indicate similarity. It is going to be similar to the triangle P primed ZQ primed. Okay, so we can see this again because angle AP primed X is equal to angle ZP primed Q primed. Again, that's opposite angles. AXP primed is an alternate angle to the angle P primed Q primed Z, and so on and so forth. Okay, so I'm not going to go through all of the details, but these two triangles are similar. Again, we've got ZY is parallel to AB, and 2ZY is equal to AB. And also it follows then that twice ZQ primed is equal to AX, and therefore twice P primed Q primed is equal to P primed X. Okay, so in other words, this point P primed cuts this line segment XQ primed at the 2/3 point from the point X. Okay, so P primed X. So let me have a look at what I did next. A P primed. Right, so XQ primed is equal to XP primed plus P primed Q primed. A lot of this stuff, by the way, I wouldn't necessarily be writing out explicitly, but it is still going on in my head. So I'm writing out as much detail here so that you can see clearly, as clearly as possible, the kinds of things that are going on in my head. But how much you write, by the way, is entirely up to you as part of your solution. So, okay, P primed X, XP primed, they're the same thing. So we get that twice XQ primed is twice P primed Q primed plus P primed Q primed, which is 3 P primed Q primed. Is this what I really want to be doing? Okay. I'm not sure that this is actually what I want to be doing. P primed, Q primed. No, sorry. That's not what I want to be doing. 2xq primed is equal to twice xp primed plus twice p primed q primed. Twice xq primed is equal to xc, or cx, and 2xp primed, 2p primed q primed, that's going to be equal to p primed x, so is equal to 3x p primed. Okay, so 2p primed q primed is equal to p primed x, or xp primed. So that means that xp primed is a third of the length of xc. So p primed, in other words, lies again 2/3 of the way along the line through c and x, along the line segment between c and x, 2/3 of the way along that line from c. Well, that's exactly what we had here. So, okay, maybe I could express it a little bit better, but we've arrived at the same result effectively. That here we had 2xp is equal to pc. Here we get 2xp primed is also equal to, what is it? Is equal to p primed c, which shows that p primed and p are the same points. Okay, so this is the pure geometrical approach. Now I've gone into a lot more detail here because maybe a lot of the people watching this video might not be so familiar with pure geometry. The kind of techniques, how they're applied and things like that might be quite new. So I've tried to spell it out much more clearly. So I don't think that I've necessarily made it look here like the pure geometrical approach is more effective or more elegant than the coordinate geometry approach. In my opinion, it is. Make up your own mind. I've got nothing against people wanting to use coordinate geometry, by the way. It's a perfectly good approach. It's just, I liked this problem because you could look at it from different perspectives, take completely different approaches to it. So the upshot is that the medians cx and az intersect at the point p primed, which turns out to be the same point as P, which is the point of intersection between CX and BY. And that proves the result, and that's the end of this video.